So, let's start with announcement. The chapter 1 homework is due on the 12th on WebAssign. The getting started with WebAssign homework is now past due. If you didn't finish it, I'll go over how you can request an extension. So, as a student, you'll see something like this. Shut up. If you go, you can look at past assignments. And in past assignments, underneath the assignment, there's a button that says request extension. And you can click on the request extension button. You have two options, request a manual extension or an automatic. I would suggest requesting an automatic extension. You'll immediately get the extension. You get 2 more weeks with a 10% penalty on all questions answered after the extension request, that you hadn't done already. So there is the extension. And I'll close the student view and go back to the slides. So, additionally, the chapter 1 quiz will be on Wednesday in the SI session. And today we have a lab, our first lab. Our first lab will be in here at 1 p.m. It'll be on density. And so make sure you're here for it. Any questions? Okay, let's start talking about geology. We finished our introduction chapter. We're going to talk about geology. So we'll start with structural geology and plate tectonics. This is chapter 21 in your book. So this is sort of the sort of overview approach for geology, starting to look at how everything works on a large scale. So modern geology is based on the idea of plate tectonics, that most of the geological processes on Earth are driven by these plate tectonics. So we'll talk about the regions of the Earth's interior, its inner core, its outer core, its mantle, and its crust. We'll look at the way we know this by looking at the types of waves, primary and secondary waves that result from movements along faults, because the way we understand what's inside the Earth is by studying how the waves from earthquakes get transmitted elsewhere throughout the Earth. And we'll talk about the difference in their ability to move through the Earth's interior. We'll talk about the lines of evidence that led Alfred Wegener to suggest that the Earth's continents have moved, including the evidence provided by continental drift, fossil records, and ancient climates. We'll talk about why continental drift as a proposal was initially rejected when it was first proposed by Alfred Wegener. And we'll look at the evidence for seafloor spreading and magnetic reversal of the Earth's poles, and how this information enhanced Wegener's proposal of continental drift and sort of completed the theory of tectonics. It filled the massive gap there was in Alfred Wegener's theory. We'll look at the differences between continental and oceanic crust. We'll talk about the characteristics of divergent, convergent, and transform boundaries between continental plates. Tectonic plates, sorry. And we'll describe examples of geologic features associated with these sorts of boundaries. We'll discuss how the movement of the Earth's tectonic plates results in geologic features, including volcanoes, earthquakes, and mountains. And we'll differentiate between the focus and epicenter of an earthquake. And we'll differentiate between the different types of faults. Normal faults, reverse faults, thrust faults, and transform faults. And we'll look at the processes involved in mountain building and tsunamis. So Geology is the study of the planet Earth, its composition, its structure, its processes, and its history. In this chapter, we're going to look at the basic structure of the Earth's interior and how that's driven. Next chapter, we'll look at more. Name? I don't know. We'll look at we'll see how plate tectonics is the primary mover of the Earth's outer shell and how it's related to mountain building, continental drift, earthquakes, volcanoes, and seafloor spreading. So in this chapter, we're going to look at the sort of big picture of the Earth. And then in later chapters, we'll focus a little more on other processes. If you want to get started on understanding some of the stuff we're going to talk about in the next couple of chapters, most of what we'll talk about in the next chapter. Amusingly enough, there's a anime coming out right now called Rory Rocks, which is about geology and mineralogy. That does some really good jobs discussing things like the rock cycle, which we'll get to in the next chapter. Doesn't talk much about plate tectonics because it's focused more on mineralogy, but yeah. So, despite many remarkable scientific advances, the vast majority of the Earth's interior is still utterly unreachable. The Earth is something like a few thousand kilometers across. The deepest hole ever dug is 12 kilometers deep, and yeah, not very big around. So we obviously didn't find out what the interior of the Earth is made of by going down there and looking directly. So the way we understood the composition and structure of the Earth's interior comes from a number of factors. By looking at the waves emitted by earthquakes and how they transmit throughout the Earth, by looking at meteorites that are thought to be leftovers from the formation of the solar system and using them to sort of work out what the starting materials for Earth were, by various spacecraft measurements of gravity and magnetic variations, and by high pressure and temperature laboratory experiments on rocks to work out what would be going on at the high temperatures and pressures inside the Earth. Just a second, I want to see if that was. Oh, no. The biggest tool, the most useful tool is probably earthquake body waves. Because much like you can do an ultrasound and send vibrations through your body to see what's going on inside you, you can do earthquakes let us do a similar thing for the Earth itself. But yeah, but we can also do detailed measurements of this local strength of gravity and variations in magnetic fields and things to get even more detail. So, but yes, the most important tool for revealing the Earth's interior are the waves from earthquakes. So during an earthquake, some of the vibrations from that earthquake travel clear through to the other side of the world, through the interior of the Earth. And in that process, they get affected by the interior of the Earth. They get bent, they can get absorbed, things like that. So by using the speed and direction of the waves from an earthquake and knowing where those waves came from originally, we can identify the types of materials through which they moved. It also helps that earthquake waves come in, the interior waves from earthquakes come in two different types. And those types have different properties and different materials. So, one of them can only go through solids. The other one can go through just about anything. So the fact that the one that can only go through solids disappears in a certain area indicates that there's a big liquid thing, which is our liquid core. So earthquakes produce two seismic waves of two basic types, surface waves and body waves. Surface waves are on the surface. They travel on the surface, the upper few kilometers of the Earth's surface. They're responsible for the most earthquake damage because they're making the ground wiggle. While body waves are transmitted in all directions through the interior of the Earth. And body waves actually come in two types. Body waves are what people are interested in when studying the interior of the Earth. So here is a short video introducing earthquakes. Let me make sure I have the right sound settings. Especially because something. Okay. I had the wrong sound settings, which good that I checked. Is this broken? Um, mhm. So this video is somehow not working. That's not right. Copy link. Well, first of all, delete this. Here. Um, so this video might be gone. I'll try and open it in YouTube. No, it's right here. That's all right. Well, for now, this should hopefully work. Yes. Sorry about that. I don't know why that's short.
April 18, 1906, California's San Andreas Fault snaps, shaking San Francisco for nearly 60 terrifying seconds. When the trembling stops, the disaster is only beginning. Gas lines rupture, setting off massive fires. Some 700 people die. Most of the city is reduced to ruins. This trembling of the ground, caused when masses of rock suddenly shift below the Earth's surface, is called an earthquake. Hundreds of little earthquakes shake the planet every day, but most pass unnoticed. They usually occur along the boundaries of the thin plates that cover the Earth like an eggshell. Driven by the heat deep within the Earth's core, the plates grind against each other along lines called faults. When the plate's motion is blocked, stress builds up. Finally, the fault gives way. The released energy races through the Earth in the form of seismic waves. Scientists record these waves on a device called a seismograph. These zigzag lines show the strength of various seismic waves. Using the lines, scientists grade earthquakes on the Richter scale. For a quake to measure one number higher on the Richter scale, it must release about 30 times as much energy as the number below it. Every year, about 100,000 earthquakes rumble through the ground hard enough for people to feel them. Of these, only about 1,000 are strong enough to damage property. But a powerful earthquake can be devastating. On average, about 10,000 people die each year as a result of earthquakes. The greatest recorded earthquake ever to hit North America measured a massive 9.2. The tremor struck Alaska on March 28, 1964. A camera on board a ship docked in Valdez recorded the draining of the entire harbor as a chasm opened up on the sea floor. There's no stopping the surface of the Earth from changing and moving, so engineers are focusing on ways to create better buildings, highways, and bridges, structures that will remain safe and stay in one piece the next time the Earth begins to shake.
So yeah, there's nothing you can do to prevent earthquakes, but you can design things to be more resilient to them. So body waves, the waves that are more interesting for scientific purposes, can be distinguished in two types by their type of motion and their speed. There are primary waves, which are compressional in nature. So the rock is squeezing and stretching. This is much like sound. And the particles move back and forth longitudinally or in the same direction as the wave is traveling. And they're also faster than secondary waves. Secondary waves are transverse in nature. The particles move side to side compared to the direction the wave is moving. So the primary waves involve compressional and tension forces. So they're pressure waves. That's the other term used for them. And the secondary waves, because they're moving side to side, those are shear forces. They're also called shear waves. Mainly they're called P and S waves. And the abbreviations work for both. Call them primary or secondary, or pressure and shear. And the particles move at right angles to the direction of the wave normal. So the other big difference between P and S waves is that S waves will only travel through solids. Basically, liquids and gases are too slippy for the sideways motion to continue. While P waves can actually travel through anything, solids, liquids, and gases. P waves travel faster than S waves and will arrive earlier at a seismic station. And this is actually really useful because it turns out by measuring the difference in time between the P wave arriving and the S wave arriving, you can figure out how far away the earthquake was. And if you do that in a few places, you can figure out where the earthquake started. And so that allows you to determine the focus of the earthquake, the point where the earthquake started. So here are some videos showing P waves and S waves. So this is an animation of P waves. So this is a P wave. You see it's a compression wave moving along the length of the material. This is just like how sound works. Now, right now you're hearing a compression wave being transmitted through air. And then this is an S wave. See how it moves side to side compared to the direction that the material is moving. Yes. It's a little different than what's going on in water, but it's closer to what you see in water. Because it's in the structure, so it's a little bit different. Water has some effects from the surface and some aspects there. And also technically water isn't exactly moving up and down, it's moving in little circles, it turns out. But it's a little different, but it's that sort of wave. Yeah, it's transverse wave. It's a transverse wave like the kind of wave you'd see on a string. It's a little closer to maybe the wave you'd see on a string. Kind of. And that video doesn't work anymore, but that was a surface wave thing. Surface waves are a lot more random. Now body waves will refract. They will bend depending on the density of the interior of the Earth. Same thing happens with any wave. Basically, well, it's usually based on density, but it's whatever affects the speed of the wave. When a wave passes from one material into another, it bends. You all experienced, have probably seen this, like if you've looked at a glass of water with a straw in it and the straw looks broken, that's light bending. In the same way. Similar things can happen with sound, with body waves, in earthquakes, from earthquakes. Primarily depends on the density of the material it's traveling through. The Earth's interior will generally increase with density, with depth. So the body waves will curve. They follow sort of big arcs. And they refract. Yeah, that's refracted. And there's sharper refractions when they go from one material to another. So geophysicists can use the travel velocity, the pattern of refraction, and the travel path to figure out the interior structure of the Earth. So here's an example of this. We look at the seismic waves that travel through the Earth. Here we have the P waves. The P waves, you'll see they sort of sharply refract when they go from the mantle to the core. But they do travel all the way through. And that refraction when they enter the core leads to an area where they don't quite make it out. While the S waves can't make it through the liquid part of the core. So there's a big shadow zone for the S waves that you never see S waves on the opposite side from the earthquake. But you do see P waves. That's part of how we figured out that there was a liquid core in the Earth. So this allows us to build up a picture of the Earth's interior. This is a simplification. The actual interior of the Earth is not so nicely perfect spheres. It's messy and weirdly shaped, but it's roughly like this. So seismic waves inside the Earth let us understand the interior of the Earth.
In this video, you're going to learn how we used earthquakes to look deep into the Earth. How deep is the deepest mine on Earth? Is it A, 1 kilometers, B, 2.5 kilometers, C, 4 kilometers, or D, 9 kilometers? It's 4 kilometers. How deep is the deepest hole ever drilled into the Earth? Is it A, 12 kilometers, B, 18 kilometers, C, 22 kilometers, or D, 28 kilometers? It's 12 kilometers. Were you close? The distance to the center of the Earth is about 6,400 kilometers, so the deepest hole is only about 0.2% of the way in. So how do we know so much about the structure of the Earth, since we have quite literally only scratched the surface? You may have seen cutaway diagrams of the Earth like this. So how do we know so much about somewhere we haven't yet been able to explore? We need to use something that will penetrate deep into the Earth and return information back to the surface. The Earth's surface is broken up into several tectonic plates, which are in constant, very slow motion. Earthquakes occur usually at the boundaries of these plates, as they move against each other. Watch our video on plate tectonics. Earthquakes create shock waves, like a bell ringing, known as seismic waves, and these travel both deep into the Earth and around its surface. Two types of seismic waves are made, and each is quite different. P waves. These waves travel the fastest and are called primary waves or pressure waves, as they arrive at a distant location first. These waves compress and stretch the rocks as they spread out. P waves pass easily through both solids like rock and liquids like magma. S waves. These slower waves arrive after the P waves, and so are called secondary waves or shear waves. S waves cause an up and down motion. They travel through solid but not liquid. Earthquakes are daily natural events monitored by seismic detector stations across the globe, which all build up a picture of how the waves travel through the Earth. This is one way of displaying the seismic waves as detected by a seismometer. Notice how the P waves arrives first. And here comes the S wave. It was found that not all of the waves started by an earthquake arrived at the seismic detectors on the other side of the Earth. P waves are detected over most, not all, of the surface of the Earth. The curved paths are caused by refraction of the P waves as they pass through rocks of different densities. Remember, P waves travel through both solid and liquid. The core dramatically alters the path of the waves as they approach or pass through it, which suggests a significant change in density from a solid into a liquid state, magma. This is how we explain the so-called P-wave shadow, and so begin to understand the structure of our Earth. S-waves have a much larger shadow zone, suggesting there is a liquid iron structure deep in the Earth they cannot travel through. Calculations can then be done to deduce the relative sizes of the layers hidden deep inside the Earth and suggest if they are liquid or solid. In conclusion, study of S and P waves led us to the knowledge that the Earth has a layered structure with a solid inner core surrounded by an outer liquid core.
So, the structure of the Earth, we think the Earth has more or less, based on, there's four main layers, four concentric layers or zones. There's also some subdivisions in here we'll talk about a little later. But there is the inner core, which is solid iron and nickel. The outer core, liquid iron and nickel. The mantle, which is mostly solid hot rock, though some of it is more fluid than others, more gooey than others. But it's rock, but it's a denser rock than the crust, which is a thin outer layer that we live on, which is the least dense rock. And they have different compositions and/or physical properties that characterize each of these layers. So the crust is a different composition than the mantle. The outer core and inner core have a different composition than the than the crust in the mantle as well. And then there's some variations in the mantle by how stiff and or soft it is. So evidence suggests the inner core is solid and composed mostly of iron, about 85%, and nickel, and has a radius of around 1,230 kilometers. The outer core is assumed to have more or less the same composition of the inner core, but it's liquid. Basically, as you go towards the center, the pressure gets high enough that it gets hotter and higher pressure, but the pressure wins out and it becomes solid. That's why the inner core is solid while the outer core is liquid. The outer core is assumed to have the same composition, but liquid, with a thickness of about 2,240 kilometers. And the mantle's composition is distinctly different from the outer core. Instead of being liquid metal, it's more solid rock. But it's rocky, and it's made of, as far as we can tell, a very denser, more iron-rich minerals, but still made of rock. The upper mantle is nearly molten, so it's sort of gooey. This is what the tectonic plates are sliding across, while the lower mantle is rocky. And then the crust, the thin, solid outer layer we live on, is called the crust. And that's made of less dense, lighter minerals. There's also the layer immediately below the crust in the mantle is also rigid, and that is what the tectonic plates are made of. We'll get into that in a bit. So here are the layers of the Earth's core.
If we could split open our planet, we would see that it is made up of various zones. The Earth is approximately 8,000 miles, or 13,000 kilometers, in diameter, from the North Pole to the South Pole. At the center, we have what we call the inner core. It is thought to be a solid metal ball, about 750 miles, or 1,200 kilometers, thick. This center core is under extreme pressure and is believed to be at least 5,000 degrees Fahrenheit, or 2,760 degrees Celsius. Surrounding the inner core is the outer core. This area is about 1,400 miles, or 2,300 kilometers, thick, and is believed to be molten or liquid rock. Nickel and iron are probably the main elements of the outer core. Next is the mantle, approximately 1,800 miles, or 2,900 kilometers, thick. Geologists think that most of the mantle is solid rock. However, towards the top of this layer, there exists an area of hot, thick, molten rock. This area is called the asthenosphere. And above this area is the cool and rigid outer shell of the Earth, which we call the crust. Geologists sometimes refer to the crust and the solid area directly below it as the lithosphere. As we take a closer look at our diagram, we see that on dry land, the crust is a mere 20 to 60 miles, or 30 to 100 kilometers, thick. The rock that is similar to the common rock, granite, makes up most of this section of the crust. And under the ocean, the crust is a much thinner layer of rocky material similar to basalt. This section of the crust is approximately 3 to 6 miles, or 5 to 10 kilometers thick.
And so that mentioned deepest hole that was ever dug, that was on continental crust. So it never made it past the crust, because it was somewhere, I mean, it was done by the Russians. It was done by the USSR. I can't remember if it was in Russia or if it was in like Kazakhstan or something. But it was in the middle of the continent. And the problem was that as they got deeper and deeper, their their drill bits kept melting. It got so hot, basically. The crust is 5 to 40 kilometers deep, thick. Then there's the upper mantle, about 670 kilometers in. The lower mantle, about 2,230 kilometers thick. The outer core, which is a viscous metallic liquid, about 2,240 kilometers thick. And then the inner core, which is solid iron and nickel, about 1,230 kilometers in diameter. I mean, in radius, thick, yeah, from the center. And the outer core, which is liquid, currents in the outer core is what creates the magnetic field of the Earth that protects us from charged particles flying at us from space. So the solar wind and such. So the Earth's crust that we live on ranges in thickness from about 5 to 11 kilometers for the oceans, for the oceanic crust, and about 19 to 40 kilometers for continental crust. Continental crust both goes up higher and down deeper. So where there are tall mountains on continents on the surface going up, there is also a deep root going down into the mantle. Oceanic crust is mostly composed of basalt, while continental crust is mostly composed of granite. Different processes that form the rocks involved lead to different types of rocks. And there's a sharp compositional boundary that exists between the base of the crust and the upper mantle. This is called the Mohorovic discontinuity, or simply MOHO. There's a sharp change in the type of rock. It becomes a lot denser when you get to the mantle. And we can detect this. And we also have some idea what mantle rocks are made of, because there are certain volcanoes that pull material from very deep and pull up from the mantle. So by studying the rocks that come out of those molten rock that comes out of those volcanoes, we can get an idea of the composition of mantle rock. So the crust and upper mantle can be divided differently if we take into account its physical properties and its behavior. The outermost layer of the crust and mantle together, so it's the entire crust and the uppermost layer of the mantle, is what's known as the lithosphere. The lithosphere is what forms the tectonic plates that move around on the softer asthenosphere beneath it. So it's solid, it's rigid. Most faults and earthquakes occur in the lithosphere, and it extends down around 70 kilometers. So this is what these tectonic plates that are moving around are made of. And beneath the lithosphere, beneath the crust, and extending down about 700 kilometers, is the asthenosphere, which is at a high temperature and relatively lower pressure than the rest of the mantle. And so because of the conditions it's in, it ends up not quite liquid, but soft and sort of flowy, sort of melty. That's a good way to sort of determine it. Sort of in between solid and liquid. So it flows on very long time scales. And so basically the lithosphere is floating on top of the asthenosphere. Is how you can think about it. And currents in the asthenosphere move the plates of the lithosphere around. So it's plastic, it's mobile, and it's essential for tectonic plate motion. And basically, Earth is one of the very few places we know of that actually has tectonic plates and plate tectonics. I think it's the only place in the solar system we found with plate tectonics. So this is the lithosphere and the asthenosphere. So we have the crust, we have the solid layer of the mantle underneath it, and then there's the asthenosphere, the soft material underneath that is driving the movement of those plates. So how did we figure out that the continents were moving? Because they're not moving very fast. We can't measure it, but it's like we're talking movement on the order of centimeters per year. Well, the first hint was that if you look at a world map, I'll just grab a globe. One of the things you can notice is that if you look at the edge of South America and the edge of Africa, they're basically the same shape. The coastlines of Eastern South America and Western Africa fit together really well. And one of the things was, is this a coincidence or were these two and other continents once attached is sort of the question. So over the past several hundred years, scientists have speculated as to the meaning of this observation and asked the question, have the continents drifted? Have they moved? And the first person to assemble a really solid collection of evidence for this was Alfred Wegener. He was a German meteorologist and geophysicist who spent a non-trivial amount of time in Arctic weather stations, which may have led to this theory. Because if you're in an Arctic weather station, you really have a lot of time to sit around and think. But in the early 1900s, he revised or proposed this hypothesis of continental drift and actually collected a bunch of really solid evidence for it. So he proposed that about 200 million years ago, all the continents were merged together into a single supercontinent that he called Pangaea. And then during the past 200 million years, Pangaea broke apart and the newly formed continents slowly drifted apart. And he found a number of pieces of evidence for this, not only the shapes of the continents, which do fit together like puzzle pieces, but he also found fossils that were the same on both sides of where the continents would fit together and geologic features that matched up, like mountain ranges. And he also found some evidence of glacial retreat that all looked like a bunch of continents. The directions all nicely fit together if you combined them up. So here is a short video showing the process by which Pangaea broke up to our modern understanding. He was correct. There was originally, 200 million years ago, there was a supercontinent called Pangaea. Turns out every once in a while, all the continents will merge together. Every once in a while, they'll all separate again. This has happened multiple times in the history of the Earth. The most recent of them was Pangaea about 200 million years ago, but there's been previous supercontinents before them. And actually things like, it turns out the Appalachian Mountains were formed by the formation of Pangaea. But here's sort of
continental drift. Let's travel back in time and watch continents move. Moving back in time, the Himalayas and Mount Everest disappear as the collision between India and Asia is reversed. Climates are changing. Australia joins Antarctica as India approaches. Going back 150 million years, the continents are joined in three large pieces. South America and Africa are on one landmass. India, Australia, and Antarctica form a second. North America, Europe, and Asia make a third. 225 million years ago, the supercontinent Pangaea exists. Let's watch this movement as it occurred going forward in time. As Pangaea splits into three large pieces, the Atlantic Ocean starts to form. India starts its race to collide with Asia. As the continents take their current locations, India and Asia collide, and the Himalayas and Mount Everest appear. What is next?
So around 200 million years ago, Pangea started to break apart. North America and Eurasia separated, South America and Africa separated, India started to move up, and Antarctica and Australia separated. So over time, about 100 million years ago, this is what we had. South America had separated from Africa. North America was separating from Eurasia. Africa was heading towards Eurasia. India was coming up towards Australia. Madagascar had separated off. Australia was separating from Antarctica. And this is the present day continental configuration. North America, Europe and Asia. India has slammed into Asia, forming mountains. South America, Africa, Australia. And this process is still ongoing. Like, you know, Africa, there's a Eastern Africa is sort of separating from the rest of Africa. There are various places where rifts are occurring. You know, the Red Sea here is caused by the separation of the Saudi Arabian subcontinent from Africa, and the Arabian subcontinent. So Wegener brought together various pieces of geologic evidence that supported his theory. There are three prominent lines of evidence that he highlighted. Biological and paleological evidence. So animals on opposite continents that are very similar, and also fossils that were the same. Continuity of geologic features and glacial evidence. The biological and paleontologic evidence was that we find present day biological species on widely separated continents that have similarities that suggest these land masses were once together. And identical fossil plants and animals have been found on a number. Though there's a few weird exceptions to that. There's some where it's like, we know this animal evolved after the continents separated, but they still somehow got over there. So some of these we have working out how things happen. And then there's also identical fossil plants and animals have been found on a number of continents. Once again, strongly suggesting that these continents were together when these organisms were alive. So this is the fossil evidence is much better evidence that these were bound together, because we find these, areas with fossils that match up. So, here, for example, we find each of these colors is a different sort of fossil, the red, green, orange, and yellow. So here the red, you can see how the red here sort of goes across South America and Africa. The green goes South America, Africa, dips into Antarctica and up into Australia. The yellow goes into South America, Antarctica, Africa. The green also goes up into India, along with the orange, goes into India and Africa. And then there are also places where they have matching mountain ranges, these purple sections. These mountain ranges match up. There's another one in South America. And there's places where they have very similar rocks that used to be together. So you get the continuity of various geologic features. So if the continents of North America, Europe, South America, and Africa all get put back together, certain geologic features connect together. So in the Northern Hemisphere, the Caledonian, Hebrides, Labrador, and Canadian Appalachians all match up to each other. In the Southern Hemisphere, the Cape and Sierra Mountains of South Africa and Brazil also line up nicely. And then lastly, there's glacial evidence. But here we have a short video about how Alfred Wegener approached this problem.
Germany, 1911. A meteorologist named Alfred Wegener was browsing through some books when something caught his eye. a list of identical plant and animal fossils that had been found on opposite sides of the Atlantic Ocean. Wegener was intrigued. How could the same species have gotten from one part of the world to another? He examined the eastern coast of South America and the western coast of Africa and was struck how the shapes of the two coastlines might fit together. The more he looked, the more links he found. Species of land mammals in East Africa also inhabited the island of Madagascar. How did that happen? Did the animals evolve in both places at once? Or did they somehow cross from one land to the other, swimming hundreds of miles across the Indian Ocean? And then Wegener saw it all clearly. He realized that all the continents in the world had once formed a giant single landmass that he called Pangaea, from the Greek Pangaia, meaning all earth. It was in Pangaea that the plants and animals found on opposite sides of the world had once shared the same home. Then, over hundreds of millions of years, Pangaea had split apart, and its jigsaw pieces had drifted to their present locations. Wegener called his theory continental drift. Wegener wasn't the first scientist to speculate that the Earth had once been dominated by a supercontinent, but he was the first to pull together all the evidence and make a strong case for it. Unfortunately, his peers weren't very receptive. There was no mechanism to explain how the continents might plow through the oceans. Continental drift was just too incredible to believe. As a result, his discovery was largely ignored.
Yeah, so the biggest problem is he didn't have a mechanism. And it took until late 50s, early 60s for that mechanism to be discovered. So here are some geologic features that match up. The Labrador and Hebrides Mountains, the Canadian Appalachians and the Caledonian Mountains, and the Sierra Mountains and the Cape Mountains match up. And so, lastly, there is glacial evidence. There's geologic evidence that suggests the southern areas of South America, Africa, India, and Australia were all covered with glaciers around 300 million years ago. And there's no evidence for glaciation at this time in Europe and North America, which indicates that the areas that have had glaciers then were further from the poles, while the areas that didn't were closer to the equator. Additionally, the directions that those glaciers receded, they left remnants that were preserved, indicate, they all sort of point in the direction they would be if they were all merged together in the way Pangaea works, for the direction they receded. So not only did we identify where these glaciers were, so they match up so they were further south, but also the way that these glaciers retreated also indicates, that, they were going this way, this way, this way, this way, this way, that kind of thing. That process of retreat indicates that they were all together, kind of. Also, there are coal deposits, where coal deposits are located. You saw that all the coal deposits, which are currently relatively far, a lot of them are kind of farish north, they're up here-ish. A lot of them used to be further south and were swampy areas. And a number of lines of evidence supported Wegener's theory. It wasn't widely accepted. It still had one massive critical flaw. Neither he nor anyone else could devise a mechanism that would explain how continental crust can move through oceanic crust. He talked about it sort of crashing through and shoving it out of the way, kind of, which didn't make sense. There wasn't a good mechanism for this. And it wasn't until 1960 that a viable mechanism was suggested by Harry Hess, with information from a number of people from before Not all the names I can think of at the time. The American geologist Harry Hess suggested a environmental mechanism to explain continental drift, and this came from the various studies of the seafloor that happened after World War II, because with all the submarine warfare and such, people got a lot more interested in what the seafloor looked like, and developed the technology to actually map the seafloor. So the mid-ocean ridge system and deep sea trenches had been mapped in fair detail by other geologists. And there was known to be a mid-ocean ridge system that spread throughout the world, and very deep trenches that were long and narrow at various locations. And understanding what these were and what they corresponded to, and combining it with paleomagnetic data, is what led to Harry Hess's model of seafloor spreading. So Hess proposed the model, the theory of seafloor spreading, where in some places, continental plates are separating apart, tearing apart the crust, leading to an upwelling of magma that makes new seafloor. While in other places, that old seafloor is sinking underneath other crust and being destroyed. So in this theory, the seafloor slowly spreads by moving sideways away from mid-ocean ridges. So there's a mid-ocean ridge in the middle of the Atlantic Ocean, steadily spreading apart, and new crust is formed. New magma wells up, cools on each side of the mid-ocean ridge as it slowly spreads apart. And dating of sediment shows that all the sediment in the Atlantic, for example, was relatively young, like less than 180 million years old. And it got older the further away you went from the mid-ocean ridge. And then at these trenches, these deep trenches, that's where one plate is sinking underneath another and melting. The entire ocean floor can be viewed as sort of a giant conveyor belt. New crust is formed at mid-ocean ridges. Old crust is destroyed at subduction zones, at these oceanic trenches. So new sort of seafloor forms and moves away from the ridges and eventually descends back into the mantle at the trenches. And so by studying these ridges and these structures, we were able to figure out the actual motion of the crust and the mechanism behind it.
Analyzing core samples and sonar readings from around the mid-Atlantic ridge, Hess made an astonishing discovery, a phenomenon almost beyond comprehension. The age of the Atlantic Ocean floor, he determined, was progressively older the further it moved away from the ridge. Harry Hess had discovered that the seafloor was spreading. He concluded that molten rock was being forced up from inside the Earth at the ridge, where it then formed into new crust on the ocean floor. Gradually, it was pushed away on either side as more molten rock continued pushing up from behind it. Hess called his great discovery seafloor spreading.
Harry Hess was in a position that he could bring it all together. Things were spreading apart and new Earth was being generated. But if you did this for long enough, the Earth should grow. And it doesn't.
The Earth doesn't get any bigger.
No. Harry appreciated the fact that if new Earth was being generated in one area, they have to be consumed or recycled in another area.
The process that recycles the crust of the spreading ocean floor back inside the Earth is called subduction.
So new crust is formed at mid-ocean ridges. It subducts under plates at other places, forming these deep oceanic trenches, and it melts once it sinks underground. So another thing that happens is this: we found this paleomagnetic data. So as new magma wells up and cools, it's magnetized by the Earth's magnetic field. And the Earth's magnetic field gets locked in place. And that's recorded in the rock. So part of the rock is magnetic, it's got iron in it. And when it crystallizes and is cooling, it becomes magnetized by the Earth's magnetic field. This is called remnant magnetism. And we also know from other places that the Earth's magnetic field every once in a while changes direction. And we know this, it flips. We know this from looking at volcanoes, it turns out, because there'll be layers of remnant magnetism in volcanoes where one layer was put down in one direction, and then the next layer is in the opposite, and so on. So it has abruptly and frequently reversed itself during geologic time. And if you look at the remnant magnetism on either side of a mid-ocean ridge or a place where the seafloor is spreading, you see a pattern that looks kind of like a barcode or like zebra stripes of alternating remnant magnetism, and it's a mirror image on either side of the ridge, and it records the spreading of the Earth. So remnant magnetism of the ocean crust reveals long, narrow, symmetric bands of magnetic anomalies on either side of the mid-Atlantic ridge or any other mid-ocean ridge. And these magnetic anomalies indicate the mid-Atlantic ridge has been continuously spreading, and the Earth's magnetic field has reversed itself many times. And the mid-ocean ridge spreading rates are in the range of a few centimeters per year. And if you want to see where the Earth is spreading apart at the mid-ocean ridge in the Atlantic, take a vacation to Iceland. Iceland is sitting along the mid-ocean ridge in the Atlantic and is being slowly torn in half. With these magnetic anomalies, basically, when the magnetic field is one way, it gets recorded, and then when it switches, it records in the opposite direction. And that gets recorded in the magnetic field you can measure from the rock. So the poles of the Earth reverse it's hundreds of thousands to millions of years. Because the magnetic field of the Earth is caused by currents in the liquid crust, those currents can end up getting knotted up and changing direction, basically.
Hi everyone. We're going to talk about the Earth's magnetic field and how the reversals in the Earth's magnetic field revealed that seafloor spreading is happening. The Earth's magnetic field creates lines of invisible force that you can't see, but that your compass needle senses. And the reason your needle points north is that these field lines emerge from the south magnetic pole and wrap around and point toward the north magnetic pole. Now, we know that the Earth's magnetic field has actually reversed, flipped around, so that these arrows would all point the other direction, coming out of the north and pointing into the south pole. And these are called magnetic reversals. They happen every few million years. The Earth's magnetic field flips back and forth through time. The reason we know this is that lava flows, like this lava flow on Hawaii, when lava flows out of the Earth, it actually, there's little magnetic minerals in the lava, and they line up with the magnetic field at the time and actually preserve, like a tape recorder, the direction of the Earth's magnetic field, whichever way it was pointing, either normal or reversed. So if we go look at a whole series of lava flows, what we'll find if we sample through the lava layers into older and older layers, we'll find some layers that are oriented with a magnetic field, say like today, and other layers, older layers that are reversed, and then still older layers that are like today. So through geologic time, the Earth's magnetic field flips back and forth, and we call these magnetic polarity reversals. Now, the way that this all relates to seafloor spreading can be realized by remembering that lava is pouring out of the Earth at mid-ocean ridges. Okay, so I want you to imagine that we're going to let this ocean basin spread, and we're going to let the Earth's magnetic field flip back and forth as the ocean basin spreads. Remember that when the lava erupts and cools down, it records the direction of the magnetic field at the time, whether it's normal or reversed, backwards or forwards. So we'll start the animation here. We're going to start it at a time when the Earth's magnetic field is like today, what we call normal polarity. And as the seafloor spreads, it's all going to get polarized in the direction of the magnetic field, shown by the blue part of the ocean floor. But now we have a reversal happening, and any new lava that erupts is going to get magnetized in the opposite direction. So you can see the little compass needles here have flipped, showing us that all this new seafloor is recording the direction of the Earth's magnetic field at a time when it was reversed. Now we'll let the Earth's polarity flip again. Any new lava that forms is going to record the polarity of the Earth at that time. So what we see on the mid-ocean ridges of the world today is a series of stripes, symmetrical stripes on both sides of the ridges of seafloor rock that's magnetized in the same direction as the magnetic field today, older rock that's reversed, still older rock that's back to normal. This pattern is impossible to explain if seafloor spreading didn't actually happen and the Earth's magnetic field didn't flip back and forth. So it constitutes some of the best evidence we have that the seafloor is actually spreading over geologic time.
So, Wegener's original evidence, the biological, paleontologic, geological, and glacial, supports the theory of continental drift. Hess's theory and evidence, remnant mechanism, supports the idea of seafloor spreading. And when these are combined, we get the modern theory of plate tectonics, which is like, started in the 60s. So it's like 60 years old, not very old. And we now know that both the oceanic and continental crusts are carried as part of a thicker layer called the lithosphere. And we have a better understanding of this process. So we now visualize ocean basins to be in a constant cycle with new crust being created at the mid-ocean ridges and old crust descending along ocean trenches. We know that the lithosphere is composed of a series of solid segments called plates, and these plates are constantly moving and interacting with other plates. And the theory of plate tectonics encompasses all of these processes. And the lithosphere is divided into about 20 different plates. So here we have a video showing sort of the process of how these plates move along the surface of the crust.
It happens because hot rock rises, heated by the Earth's core.
The Earth's core has
Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart. And it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption.
Well, that is one of the primary ways that volcanoes plate.
The remarkable cycle is complete.
So here are the 20 or so plates. There's some big plates like the North American plate, the Pacific plate, the South American plate, the African plate, the Eurasian plate, the Indian Australian plates, but there's also smaller plates. Like there's this tiny plate here that's off the coast of the Pacific Northwest. There's the Cocos plate, there's the Caribbean plate, the Nazca plate down here, Saudi Arabian plate, things like that. So there's about 20 total plates. And they vary in size. And the most active areas of the Earth's crust are along the boundaries between the plates. Continental crust is primarily composed of silica-based minerals, which give it a lower density than oceanic crust. While oceanic crust is composed of magnesium iron-rich basaltic rocks, which gives it a higher density than continental crust. And there's three main types of plate boundaries, where two plates are spreading apart. That's called divergent. This happens along mid-ocean ridges, where the two plates are moving apart, or other places where two plates are moving apart. Like the African Rift Valley when it's happening on continental crust. But divergent is where two plates are spreading apart. Convergent is where two plates are driven together and one plate usually one plate gets consumed as the more dense plate sinks under the less dense plate. And then transform boundaries are where two plates are sliding against each other. Crust is neither consumed nor destroyed at these, but you do get lots of earthquakes. So the most famous transform boundary in the world is the San Andreas Fault in California, causing all those earthquakes there. And we are just about out of time. So the layer that the Earth is, the moving plates is floating on is called the aethnosphere, this higher temperature layer. It's basically solid, but it's so close to its melting temperature that it's relatively plastic, it easily deforms, and it moves over long time scales. It's much more easily deformed than the lithosphere. And so you can think of the lithosphere as floating on top of the aethnosphere. I think I'll stop there for today. I'll see you all at 1 o'clock for the lab. You need to be here to do the lab. The way labs work is we do the lab, then you have a week to turn in the lab report afterwards. So I'll see you all at 1. Have a nice day. Let's see, escape. Stop.